Apotus, the enigmatic moon of Saturn, is gradually edging toward the planet's dazzling rings at a pace of roughly 3.2 kilometers per second. Data gathered by the Cassini spacecraft suggests this gradual shift might span millions of years before it fully plays out. Even so, the alterations it's sparking in the rings right now are sparking transformations that stretch the limits of comprehension. Streams of dust, shattered pieces, and unusual substances are getting ejected, prompting researchers to grapple with pressing inquiries. Might Apotus someday merge fully into Saturn's rings? Or could this encounter herald a fresh chapter in our grasp of the cosmos? The enigmas encircling Apotus don't just draw the gaze of experts. They upend our foundational ideas about cosmic dynamics. Moreover, the odd contradictory path it's tracing could provide the vital clue to revealing Saturn's most profound enigmas. For billions of years, a subtle yet mighty evolution has been at work. It's a clash without blasts or dramatic breaks, but one so steady it could redefine this moon's destiny. What renders it so daunting is precisely its unhurried persistence and resilience. This isn't like the collisions we typically picture in human terms. To grasp it, we need to shift our focus from Apotus's terrain and turn toward a diminutive moon that's driving the action. Phoebe. Phoebe circles Saturn in reverse, a telltale sign of something snared from afar, maybe from as remote a zone as the Kuiper Belt. Packed with carbon, it's shadowy, icy, and delicate. Across eons, tiny meteoroids have hammered its exterior, flinging out vast quantities of dust specks. Rather than scattering away, these bits gradually built a massive formation, the Phoebe Ring, Saturn's biggest dusty loop, extending from around 6 million kilometers out to over 12 million kilometers. Though incredibly sparse, its vast expanse means the overall dust mass is hefty enough to affect anything crossing its path. Apotus's orbit lies squarely within the swath patrolled by the Phoebe Ring. Yet the dust doesn't just settle on Apotus unaided. It requires a hidden nudge. That nudge comes from sunlight. Solar photons barrage the dust particles, bumping into each one and generating a gradual pull called the Poynting-Robertson effect. Under this ongoing pressure, the dust sheds orbital momentum and spirals steadily closer. At the same time, Apotus circles Saturn forward while Phoebe's dust drifts backward, yielding a tremendous speed difference between them. Consequently, each minuscule feather-light particle hits Apotus's forward-facing side with sufficient force to alter its fine details and stick fast. It's akin to a vehicle racing through the dark, its glass front gathering every bug along the way. On this grand scale, Apotus serves as that collector, compelled to slice through Phoebe's backward-moving dust flow with every circuit. Cassini captured the clearest proof of this dynamic up close in 2007 during its pass by Apotus, spotting a shadowy veneer just centimeters to a meter deep, far slimmer than anything from internal processes. Fresh craters revealing gleaming, untouched ice underneath confirmed it. This shadowy veil isn't original rock but an added layer, built up externally, speck by speck, atom by atom, across billions of years. Strikingly, simulations from 2023 and 2024 mapped Apotus's trajectory through the Phoebe Ring with pinpoint accuracy, revealing that its forward side sits right in the densest dust zone, its spin and alignment position, it ideally to catch this relentless barrage. But this interaction goes beyond mere surface buildup. As the shadow thickens, it soaks up more solar heat, warming those spots and sparking the ice below to vaporize. Should this persist for another few billion years, 2024 projections estimate about 100 meters of ice vanishing per billion years on average. Seemingly negligible by our standards, but immense across the solar system's timeline. This points to a deeper insight. Celestial crashes aren't always cataclysmic bangs. Often, the subtlest brushes wield the greatest change over time. Those hushed dust motes, silent and dim, gain the might to remake a celestial body when eternity is their ally. In the end, might Apatus fade away. As ages pass, its icy exterior could wear thin, its form slowly compromise. Far in the remote future, particles eroded from Apatus could integrate into the expansive rings encircling Saturn. Approaching Apatus draws us into an intriguing contradiction. This satellite, divided by two starkly contrasting hues, seems like fragments from wholly distinct planets. The shadowy zone, known as Cassini Regio, after the astronomer Giovanni Cassini, dominates about 40% of the terrain, with an albedo ranging from 0.03 to 0.05, resembling a landscape coated in tar. Sunlight striking, it appears to get swallowed up entirely. By comparison, the luminous half bounces back illumination at an albedo of 0.5 to 0.6, almost matching the high reflectivity of Enceladus, among the most luminous objects in our solar system. These opposing sides of the moon contrast so sharply that isolated without background, one could mistake them for origins on separate celestial bodies. Typically, on other satellites, substances blend together. Thermal effects trigger sublimation. Ice shifts position, and solar winds wear away features, blending hues and surfaces into smooth gradients. Yet, Apatus defies this pattern. Its divide between illuminated and obscured areas lacks any gradual shift. No fade from gray to dimness, nor from pristine to faint. Rather, it jumps abruptly from gleaming frost to utter ebony grit. Analysis of data from the Cassini probe, revisited in 2023, indicated elevated levels of carbon and intricate organic molecules like PAHs in the dark area, along with indicators akin to particles from the Phoebe ring, that vast dusty halo orbiting Saturn, originating from the backward-moving moon Phoebe. This evidence establishes that the shadowy veneer isn't inherent to Apatus. It's an overlay from outside. But the enigma runs deeper. This covering is remarkably slender, spanning just centimeters up to a meter thick. Interactions among warmth, frost, and duration form a glacial rhythm imperceptible across a single human lifetime, with Apatus completing a rotation every 79.3 days. A single face endures prolonged solar exposure. Notably, the Cassini Regio soaks up the greatest amount of heat. As the obscured exterior heats up, underlying ice starts to vaporize, emitting faint gases from an otherwise static realm. As the frost recedes, more of the dark particles surface, boosting heat intake and fueling a reinforcing thermal spiral. Such a self-perpetuating mechanism enables Cassini Regio to hold its profound gloom, enduring across eons. On the other hand, the released gases don't dissipate. They drift toward the chillier, radiant side. There, they solidify and build up as new coatings of clear ice, amplifying its intense shine. This points to a fundamental reality. Apatus's glowing portion wasn't an initial endowment. It formed gradually, atom after atom, across billions of years, as wandering vapors condensed in the frost. In practical terms, the light side keeps gaining brightness over time, even as the dark side plunges further into obscurity. Computer models of heat dynamics, released in 2022, demonstrated that a POTUS hosts the most intense such loop detected on any solar system object. In this place, radiance and shadow transcend superficial traits. They emerge from an age-old clash of forces: radiation versus substance, warmth versus frost, buildup versus decay. Remarkably, all this occurs in virtual quietude. Absent are fierce impacts, crumbling icy ledges, or explosive vents. Just fine particles, stellar rays, and the passage of ages. These understated elements, intertwined, produce one of the grandest displays in planetary realms. Still, this heat-driven cycle represents just one facet of a POTUS's evolution. For right at the heart of this vivid light-shadow boundary lies a landform that baffles experts. A mid-latitude ridge soaring up to 20 kilometers, aligned with uncanny accuracy along the equator, and extending over 600 kilometers. Straddling the unseen processes of wear that stretch across geological epochs, POTUS bears a mark so singular that NASA labels it unprecedented in the solar system. A vast equatorial chain of peaks spanning almost the full girth of the moon, rising like a timeless barrier across a realm already cleaved apart. No Jovian moon, no orbiter of Uranus or Neptune, nor even the far-flung frozen relics beyond harbors anything similar. Solely Apatis claims this immense backbone, a marvel that Cassini probed directly in 2007, immediately identifying it as a narrative alien to routine paths or standard formation mechanisms. Stretching across 1,600 kilometers, what this immense ridge measures about 200 kilometers in width and climbs to heights approaching 20 kilometers in certain spots, surpassing Mount Everest in sheer elevation. What puzzles researchers most is its remarkably precise location. It aligns perfectly with the equator, deviating by not even 1 degree. Such exactness is uncommon in nature without the influence of dramatic occurrences from the solar system's formative era. Absent any plate tectonics, internal pressures, or rising lava from deep within, what force could elevate this icy barrier spanning thousands of kilometers? Experts have put forward 2 primary theories, and despite their differing processes, both point to a shared outcome. The ridge ranks among Iaptis's most ancient enduring landmarks, potentially originating over 4 billion years ago. Under the classic theory, the young Iapetus might have spun much quicker than now, possibly boasting a 16-hour day instead of the present 79.3 days. That intense spin would maximize centrifugal effects at the equator, exerting outward pressure on the moon's pliable, ice-dominated shell. Should Iapetus's exterior have remained somewhat liquid or fragile back then, it couldn't have withstood the expansive tug. The body would swell like a rapidly twirling orb, creating a thick band around the middle. Eventually, gravitational pulls from Saturn would decelerate the rotation, allowing the surface to solidify and lock into that elongated form, yielding a frozen, icy crest. This explanation accounts for the feature's vast extent, the moon's distinctive walnut-like profile, and the consistent composition between the ridge and nearby areas. Yet it leaves gaps. How does a yielding initial form retain 20-kilometer peaks after hardening? And why does the protrusion appear as a crisp edge instead of a gradual equatorial mound, akin to those on swiftly rotating worlds? These unresolved issues lend greater appeal to the alternative idea. Here, a tiny satellite orbiting Iapetus, or some other frozen object, might have shattered under tidal stresses, generating a tiny ring encircling the Moon, much like Saturn's grand system, but on a minuscule scale. Positioned inside Iapetus's roque limit, the debris couldn't regroup into a satellite. Gradually, atmospheric drag in orbit and collisions with the frosty exterior would draw the ring down. All particles would settle solely at the equator. Simulations from 2024 indicate that the ridge's elevation, breadth, and edge sharpness match this ring debris infall model exceptionally well, a phenomenon unfolding over tens of millions of years. Should this prove true, Iapetus once sported its own ring, and the equatorial bulge isn't just a structural leftover. It serves as a chronicle, recording hints of swift ancient spins, debris from a huge impact, signs of disrupted orbits, and maybe even echoes of a vanished companion moon, free from tectonic reshaping, precipitation, or gusts to wear it down. The ridge has persisted largely intact for billions of years. It endures today, not just bisecting the moon's terrain, but marking a pivotal historical divide. The era before and after it settled into the frigid, motionless state we observe now. In Iapetus's harsh environment, ice at such frigid levels turns remarkably durable, nearly as solid as stone, and around -143 degrees Celsius, frozen substances can endure sustained strain without buckling. Lacking substantial internal warmth or regular thawing, the formation has held its contours across geological ages. The ridge persists because Iapetus embodies utter chill and utter quiet, ideal circumstances for eternity to fossilize all things into permanence. Far beyond Iapetus's top enigma, this equatorial spine unlocks insights into the moon's full tectonic and orbital development. Yet, the tale continues as this monumental feature also faces the gradual celestial wearing that subtly transforms the whole world. Central to this heat-driven cycle is a straightforward but far-reaching reality. Iapetus's day spans 79.3 Earth days. Consequently, every surface spot endures prolonged solar exposure. Unlike Earth's brisk light-dark rhythm, there's no swift chill-off, no breezes or air to even out warmth. Thus, once an area soaks up rays, it clings to that energy, long enough for lasting alterations to emerge. In the shadowed Cassini Regio, the ultra-low albedo of 0.03 to 0.05 causes nearly total light absorption. While the overall warmth buildup seems minor compared to terrestrial norms, keeping surfaces dozens of degrees below freezing, water ice as the dominant substance means even slight warming sparks sublimation. Strikingly, data from Cassini's 2007 observations show that the carbon-rich dust blanketing the shadowed area measures just a few centimeters deep at most, no more than 1 meter. Sunlight readily penetrates this thin layer to reach the underlying ice. When that ice turns to vapor through sublimation, additional dust accumulates in its place. Consequently, the shadowy coating builds up, capturing greater amounts of thermal energy. A thermal simulation from 2022 determined that Iapetus boasts the most powerful thermal feedback mechanism documented anywhere in the solar system. No world satellite or space rock displays such a persistent and enduring pattern. Iapetus's feeble gravity, combined with its razor-thin atmospheric pressure, allows water vapor to glide effortlessly over the landscape, resembling an ethereal mist in motion. Upon arriving at the chillier bright side, this vapor solidifies back into pristine ice. This process generates a unique effect unseen on other satellites. Iapetus is steadily relocating ice from its dim half to its luminous half. Viewing it as a vital entity, one might picture it gently moving substances from warmth to frost, akin to a planet inhaling and exhaling at a glacial pace. The refreezing of ice across the bright region safeguards its gleam, while gradually enhancing its reflective properties with each cycle. Boasting an albedo between 0.5 and 0.6, the illuminated side acts as an enormous frozen reflector, deflecting the bulk of incoming solar rays and maintaining temperatures so low that sublimation hardly takes place. In contrast, as the dark side steadily sheds its ice, the bright side receives constant resupply. This inherent division arises from the core interactions of frozen water, illumination, and gaseous diffusion. What's even more remarkable is how this cycle extends beyond mere hues and shine to reshape Iapetus's landscape directly. Sublimation renders the ground spongier and more fragile, priming it for dust adhesion and heightening its susceptibility to alteration from minor meteorite strikes. The bright side, by comparison, grows firmer and steadier, serving as a frigid vault that holds the moon's relocated frozen reserves. On a deeper level, this duality transcends superficial traits, emerging as a dynamic power that reconfigures the underlying composition. The mechanism is gradually sculpting Iapetus's exterior, not through molten rock or tremors, but via radiance, darkness, and the passage of eons. Insights from the Voyager and Cassini explorations gradually uncovered a disquieting reality. Iapetus stands apart from Saturn's standard satellites, challenging conventional understandings of how frozen objects originate and develop. Begin with its low density of roughly 1.2 grams per cubic centimeter, far below that of Titan, Rhea, or Dione. This figure indicates that about 75% of Iapetus consists of water ice, the remainder being lightweight stone-like substances. Lacking signs of past internal warmth that could have liquefied or separated its components, Iapetus has stayed largely pristine from its birth over 4 billion years in the past. Its form adds yet more enigma. Space probes, full views of Iapetus, revealed a walnut-like profile, with a pronounced equatorial bulge. Such contours arise only from exceptionally fast rotation in antiquity. Simulations propose it once completed a turn every 16 hours until Saturn's gravitational pull decelerated it to today's 79.3-day rhythm. Back when Iapetus retained enough heat to remain somewhat pliable, that swift whirl expanded the midsection and, cooling, locked the irregularity in forever. This points to an origin story, distinct from contemporaneous large moons. Yet, if its outline seems odd, the exterior proves odder still. The abundance of craters, from vast ones spanning hundreds of kilometers to countless micropocks, signals an extraordinarily aged surface. Certain areas could date to 4 to 4.3 billion years, aligning closely with the solar system's own antiquity. It represents a realm frozen in quietude, enduring next to no resurfacing for eons. Absent cryovolcanism, absent renewal layers, absent subsurface movements. Its path around Saturn, at 3.56 million kilometers distant, almost triple Titan's range, positions Iapetus outside the grip of the gas giant's magnetosphere and radiation zones. Such remoteness lends it an air of separation from the vigorous forces molding its neighbors, evoking a lone relic wandering independently. The orbit's sharp 15-degree tilt against Saturn's ring plane amplifies this notion. A 2023 JPL study posits that this odd angle hints at Iapetus being ensnared in the young solar system's chaotic early days. This suggests that Apophis originated in some distant location, likely amid a zone teeming with small frozen objects disrupted by powerful gravitational pulls. In the turbulent phase of planetary reshuffling, known as the period outlined in the Nice model, Apophis got pulled into Saturn's gravitational grasp and eventually stabilized in its current path. Composed mainly of ice making up 75% of its mass, it lacks a distinct stratified interior. Resembling a body caught in a whirlwind and instantly preserved, it features a crust, nearly as ancient as the solar system, and follows an orbit tilted so dramatically that it feels like an outsider to Saturn's family. Together, these traits create a profound puzzle. Apophis acts like a relic from the solar system's dawn. However, it also shows marks of vigorous energies originating from beyond Saturn's influence. Out of this enduring oddity arose something unparalleled across the solar system. The starkest contrast in brightness ever observed on a celestial body. Far from the fleeting change that Giovanni Cassini once assumed, this is a profound, enduring result of its internal makeup, orbital path, and exchanges with a nearby haze of particles. The pull between Apophis and Saturn's rings isn't just a captivating celestial event. It serves as a striking showcase of the cosmos's constant motion and transformation. Thanks to its eccentric trajectory and sharp 15-degree lean, Apophis is locked in a languid impact that inches along, barely noticeable, but heading irreversibly toward the ring's outer boundary. This steady intake of debris and alteration of the ring's form offer real-time proof that even the most venerable moons can't escape the ever-active principles ruling their stellar environment. The gradual shift in its orbit, playing out across eons, highlights how delicate even the seemingly eternal formations appear when seen through our brief human perspective. Though the changes unfold over vast geological spans, their end is inevitable. Apophis, this isolated icy realm, is penning its final cosmic tale by integrating into the majestic framework of its host world, embodying the principles of evolution and tidal forces that mold every fragment of substance in the vast cosmic void. This narrative drives home a universal truth. Stasis has no place in the cosmos. Each planet drifts toward a conclusion forged by pull of gravity, passage of ages, and the quiet evolution of stellar forces. Venus, often dubbed Earth's twin, stands out as the solar system's most unforgiving environment in a twist of irony. Temperatures there can liquefy lead on its surface. The air pressure would flatten a submersible craft, and the atmosphere hangs heavy with clouds laden in potent sulfuric acid. Still, this very ferocity fueled the Soviet Union's unyielding pursuit across more than 30 years. Beginning with the initial setbacks of Venera 1, 2, and 3, through to the groundbreaking feat of Venera 13, the initial lander to touch down on Venus and endure for 127 minutes amid the hellish terrain, relaying unprecedented visuals, audio, and analytical readings. In 2012, a Russian researcher asserted that images from Venera 13 showed some form traversing the Venusian landscape. Though experts largely rejected the claim, it planted a seed of doubt. Could the Soviets have glimpsed something remarkable on Venus after all? Here we turn back time to explore the Venera saga, where discovery, geopolitics, and enigma intersect. The Soviet push to probe Venus via the Venera Initiative was a fierce contest against the boundaries of physics and technology. Venus, burdened by its ultra-dense air, blistering highs of about 470 degrees Celsius, sufficient to dissolve lead, and forces akin to 92 times Earth's sea depths, turned into humanity's toughest proving ground. Initial Soviet efforts largely faltered. Venera 1, 2, and 3, sent aloft from 1961 to 1965, failed to fully relay their findings. Teams soon grasped that conventional builds couldn't shield sensitive instruments from the world's searing heat and compressive might. Venera 3 marked the debut of a man-made device striking another world's ground. Yet its silence after arrival highlighted that mere touchdown wasn't enough. Venus demanded innovations in design and resilient materials. A key breakthrough hit in 1967 with Venera 4. At last, a lander pierced the atmosphere, beaming data all the way down. Venera 4 yielded the initial precise insights into the air's makeup and layers. An engineering milestone, though the craft succumbed to the crushing depths short of the surface. The height of achievement came in 1970 with Venera 7. Soviet designers overhauled the lander design entirely, crafting it as a robust titanium orb, fortified to endure pressures well beyond original projections. Constructed akin to a submarine for space, it housed delicate sensors within a sturdy, pressure-resistant casing. Even with just 23 minutes of functionality, Venera 7 verified the surface environment of the planet and demonstrated that human ingenuity could hold up against such unforgiving surroundings. Then, in 1975, Venera 9 and 10 marked a fresh breakthrough by transmitting the initial monochrome photos from Venus's surface. For the first time, these shots unveiled a tangible vista. Jagged, fissured stones beneath a foggy yellowish-orange sky, resulting from light diffusion amid dense clouds of sulfuric acid. Developing an imaging setup capable of operating amid Venus's intense heat and compression stood as an engineering marvel that outstripped the technological reach of every other country then. The highlights of the entire Venera initiative arrived via Venera 13 and 14 in 1982. Venera 13 broke records by lasting 127 minutes on Venus's ground, a short span by our standards, yet an impressive feat given the planet's brutal climate. In that interval, it carried out crucial experiments, snapping the debut color pictures that exposed intricate panoramas of dull brownish stone landscapes and a blazing orange heavens. Humanity finally picked up audio from an alien realm, the subtle howl of breezes slicing through the heavy air. With a custom drill, it gathered dirt from the surface and examined its makeup using X-ray spectroscopy, yielding essential insights into Venus's rock formation past. If the Venera program's feats signaled a daring statement, the insights it yielded whispered enigmas, sketching a picture of an abandoned planet. Humanity at last caught a peek at Venus's exterior, not merely its severity but a flood of unresolved puzzles. Probes Venera 9, 10, 13, and 14 supplied landmark visuals which weren't picturesque scenes but raw glimpses of a lethal domain. Drenched in subdued orange-yellow glow sifted through a thick aerial blanket, the ground looked stark and empty, surpassing even experts' expectations. The most captivating elements were the keen-edged stones and split slabs strewn over a layer that seemed blanketed in fine powder or grit. The persistence of those blade-like contours on the rocks continues to baffle. Here on Earth, elements like wind, rivers, and various weathering agents swiftly soften pointed formations. Venus lacks standing water, yet its ultra-thick air acts as a potent medium, whipping up gales fierce enough to grind away features. Then why preserve these boulders in their sword-sharp forms? This suggests that the forces shattering or shaping these rocks happened not long ago, or that Venus harbors some surface process, physical or chemical, that offsets the wear. Even now, those scarce direct shots from Venera hold oddities without clear answers. A number of experts, among them ex-Soviet specialists, have noted peculiar forms that flicker in and out across sequential images from identical drop zones. Could they be camera errors, fragments from the craft, or perhaps something odder? The most captivating theory, proposed by a handful of researchers, posits that the angular patterns or fleeting items in the photos might hint at resilient life forms enduring extremes. Though most in science reject this due to the planet's intolerable heat and squeeze, the wonder lingers. What sparked the peculiar blotches or subtle streaks in Venera 13's vivid shots? Landing fresh probes on Venus isn't straightforward these days. But progress has shifted elsewhere. Distant scrutiny, cutting-edge observatories such as James Webb, teamed with NASA's and ESA's radar efforts, are re-examining the world. Employing tailored infrared bands to pierce select cloud veils, James Webb probes the air's makeup and even bounces off surface features in areas once probed by landers. Today's radar systems, especially those from the Mellon Endeavour, have mapped out 98% of Venus's relief in fine detail, spotting craters, flatlands, and enormous fault lines. Yet, the subtle dust cover and keen rocks that Venera documented stay one of a kind, beyond radar's grasp. Experts now aim to leverage this archive to pinpoint the substances behind the bizarre reflections picked up by radar and JWST, particularly on higher ground. As a result, those 1970s images hold greater worth today than ever. These enduring remnants form pieces of an immense enigma, serving as a stark indicator that humanity has barely scratched the surface of Venus's enigmas. Although evidence from the Venera missions strongly suggests that life on Venus's surface is impossible. A provocative assertion surfaced years afterward, defying established scientific views and igniting widespread interest. At its core, this narrative explores how grainy photographs obtained in harsh circumstances lend themselves to diverse interpretations. In 2012, Dr. Leonid Kazan-Falidi, an experienced researcher at the Russian Space Research Institute with hands-on involvement in the Venera missions, released a contentious discovery after scrutinizing photos from Venera 13, captured in 1982. He reported spotting features that seemed to shift positions and alter forms across images snapped just minutes apart. The most eye-catching element, as Kazan-Falidi highlighted, was an intricate form, akin to an arthropod, that materialized in a single shot and disappeared in the subsequent one. He posited that it might represent signs of an extremophile organism, able to endure Venus's intense heat and pressure, possibly via a bodily or molecular makeup wholly foreign to terrestrial life forms. Yet the global scientific establishment largely rejected this idea, chalking it up to errors in perception and imaging glitches. The Venera photos suffered from very coarse detail and intense data squeezing to relay signals over vast cosmic gaps back to our planet. Subtle features and unclear outlines were prone to false readings. Experts generally agree that the form was likely just a shielding cover or hardware fragment knocked loose from the Venera 13 probe amid its landing. Any perceived motion might stem from gusts or slight adjustments in the probe's position. Our minds instinctively hunt for recognizable designs, particularly those evoking people or creatures. That arthropod resemblance could easily arise from a stone lit in a way that mimics a scorpion. Interest surged anew in 2020, following a major revelation in research. Instruments identified notable levels of phosphine in Venus's upper atmosphere, roughly 20 parts per billion. On our world, this poisonous substance arises mainly from anaerobic life processes or human-made operations. Studies show that typical reactions, be they volcanic, electrical storms, or rock interactions, fail to account for the detected phosphine amounts in Venus's air layers. Such findings position phosphine as a possible indicator of biology, hinting at unseen microbes flourishing amid acid-laden cloud particles through some radically distinct metabolic pathway that yields phosphine as waste. Even with this intriguing data, doubters emphasize two formidable hurdles: limited water availability and high acidity. Venus's cloud cover lacks free water, featuring instead dense sulfuric acid spheres. Survival there would demand armor-like exteriors or groundbreaking biochemical tricks to substitute for water in cellular fluids, something unseen in any Earth life. The toughest challenge might be the dire lack of unbound water molecules. Sulfuric acid does hold water, but nearly all is locked in chemical bonds. The free water suitable for life processes in those acid particles is vanishingly small. By way of example, Earth's hardiest dry-adapted species still need a water activity, AW, of 0.585 or higher, to keep proteins and cell walls operational. Venus's conditions are orders of magnitude more arid than what any documented life can tolerate. In addressing how phosphine could coexist with such unforgiving surroundings, researchers have floated daring ideas about biology. For instance, one theory holds that tiny organisms persist aloft in the clouds, entering a spore-resembling hibernation when swept into sweltering, harsher zones below. Fierce air currents would then lift them back to temperate heights, allowing revival and multiplication in an ongoing loop. A bolder notion envisions Venusian organisms developing a non-water-centric chemistry, perhaps relying on thick sulfuric acid or alternative substances to build durable, acid-proof frameworks. Upcoming expeditions, including NASA's Deep Atmosphere Venus investigation of noble gases, chemistry, and imaging, plan to launch instruments into the clouds. Key goals include exact tracking of phosphine and minor gases, plus sampling cloud particle makeup and water vapor across varying elevations. Such probes will probe the rationale behind viewing these cloud zones as viable for habitation and the molecular obstacles confronting potential dwellers. Investigating Venus is inherently linked to the examination of orbiting bodies across the solar system, since both highlight key dynamics of physics under harsh conditions. Works like the Comet Atlas provide essential insights. This comet stands out as a vivid illustration of frozen substances clashing vigorously with their cosmic surroundings. When nearing the Sun, it faces pressures from gravitational pull alongside electromagnetic waves and solar particles. A primary hurdle for colonizing Mars stems from its absent planetary magnetosphere and sparse air cover, which expose the surface to intense levels of harmful cosmic rays. In opposition, Venus provides inherent protection. At approximately 50 kilometers up, the air's thickness blocks nearly all energetic particles. Exposure to radiation in that zone is thought to match or even fall below the doses faced by crew on the International Space Station in Earth's lower orbit. Such conditions remove the demand for bulky, costly barriers like regolith or liquid shields required for Mars bases. thereby streamlining habitat engineering and cutting build expenses. Variations in gravitational force play a vital role in sustaining human health over extended space stays. Mars's ground pull equates to just 38% of Earth's, and extended exposure to reduced or negligible gravity triggers profound biological problems such as muscle wasting, skeletal deterioration, eyesight problems, and alterations to immunity. In Venus's upper layers, inhabitants would encounter conditions much closer to Earth's norms, minimizing threats to skeletal and muscular systems and positioning Venus as a superior option for enduring colonies and off-world childbearing. Around 50 kilometers elevation, heat levels hover from 27 degrees Celsius to 37 degrees Celsius, with atmospheric pressure close to 1 atmosphere, a substantial boon for builders. Suspended habitats wouldn't require resilience against vast pressure gaps. Rather than crafting stiff suits or enclosures to endure crushing forces, setups could focus on enclosures with scrubbers and simple breathing aids to counter acidic fumes. Since respirable air weighs far less than the ambient gases, an enormous balloon containing it could produce ample buoyancy, enabling steady levitation and height control without ongoing power use. The toughest technical issue involves crafting the envelope's materials. The exterior coating has to fulfill 3 concurrent demands: endure potent sulfuric acid within the cloud deck, endure mechanical stresses and fierce gusts, and resist breakdown from strong UV light, particularly in the upper reaches. Materials like Teflon or premium fluoropolymers lead the options. Layers of Kevlar or carbon nanotube weaves would be woven in to manage tensions and gales. Venus's relevance for upcoming ventures reaches past our system. It acts as a perfect archetype for probing exoplanets akin to itself, especially those bound in tidal locks. Venus exemplifies a world that crossed the point of water loss and locked into an unescapable heat cycle. Probing inert gases and hydrogen variants in its air via projects like Da Vinci Plus holds the clue to tracing a formerly livable world slide into a scorched wasteland. The planet's rapid atmospheric spin lets experts simulate warmth distribution and power flows on tidally locked bodies. On such realms, the sunlit face bakes while the dark side ices over. This swift circulation evens out the climate, demonstrating how a heavy air envelope can self-balance, thus broadening the livable band on tidally locked orbs to milder states. To wrap up, Venus transcends mere travel spot. It's a stellar hub where cutting-edge tech trials pave the way for our species' lasting spread across the stars. Reflecting on Venus probes' history reveals the Soviet Venera efforts as a landmark feat, marking the initial human artifacts to touch down intact on an alien world. This underscores Venus as an innate testbed for brutal reactions. Its dense acid-laden mists, corrosive downpours, and CO2-heavy envelope have forged it into a fiery inferno, a far cry from its ancient origins. Soviet reports once suggested spotting animated forms suggestive of biology in early Venera photos, though global experts mostly rejected these as glitches from signal noise or wind-sculpted stones. In recent years, the detection of phosphine, a possible indicator of biological activity in the chilly upper atmosphere, has sparked fresh discussions about the possibility of life on Venus. Our mysterious neighbor Venus stands ready for renewed exploration. NASA's forthcoming missions, including Da Vinci Plus and Veritas, will mark the initial attempts to dispatch probes that soar through its atmosphere, offering detailed analysis and mapping of its surface like never before. Following these ventures goes beyond pure science. It's a quest to explore the very limits of what constitutes life. By revisiting the enigmas the Soviets encountered and, crucially, studying atmospheric dynamics that might safeguard our planet Earth, we push forward. Proxima Centauri, the star nearest to our own, sits 4.2 light-years distant from Earth, a tremendous gap that demands an extraordinary span of time to traverse. Venturing beyond the solar system requires overcoming two primary hurdles. For starters, the velocities attainable with today's chemical rockets fall woefully short. Moreover, the power needed would need to multiply by thousands to escape the sun's formidable gravitational grasp. Studies on ion thrusters, nuclear fusion drives, and ambitious concepts like warp drives that might fold space-time are steadily advancing. Still, these innovations represent merely the opening moves in an extended odyssey, hindered by numerous physical and technical obstacles. And, should we someday master this feat, might humankind transform to endure the severe rigors of deep space? Beneath these technological inquiries lurks a deeper wonder. We should gaze toward a horizon where the unattainable draws nearer. The solar system resides inside unseen protective spheres. The heliosphere and its farthest frontier, the heliopause. The heliosphere encompasses the expansive zone where solar wind clashes with the sparse interstellar gas and dust, creating a safeguarding barrier around our worlds. The heliopause signifies the outermost reach of solar dominance, the spot where solar wind's force diminishes, unable to resist the interstellar medium's outward force. NASA's Voyager 1 and 2 spacecraft have furnished remarkable revelations about these distant realms. Voyager 1's passage across the heliopause in 2012 unveiled a plasma-rich area denser than anticipated, where robust interstellar magnetic forces resist the heliosphere's expansion. Subsequently, Voyager 2 showed that this frontier isn't a clean divide, but a chaotic, ever-shifting interface. Such findings have reshaped our view of the solar system while emphasizing the formidable task of piercing this unseen barrier. Past the heliosphere stretches the Kuiper Belt and the puzzling Oort cloud, which expand the genuine dimensions of our solar system amid the Milky Way. The Kuiper Belt, situated beyond Neptune's path, forms a huge region brimming with billions of frozen remnants, the origin point for numerous short-period comets. In this area, separations between bodies are immense, underscoring the vast expanses even light must span. Sunlight requires roughly 5 hours to arrive at the Kuiper Belt's outer limit. Even further out, along the system's extreme perimeter, floats the Oort cloud. This enormous spherical envelope holds trillions of icy chunks and stony debris, thought to generate long-period comets. It could stretch to almost 1/4 the way to the closest star. As a result, sunlight would take thousands of years to penetrate it, and thousands more to touch the Oort cloud. Probing the Kuiper Belt and Oort cloud transcends mere research. It offers a profound viewpoint, contrasting our solar system's actual size against the Milky Way's immense canvas. Nevertheless, the profound remoteness to the Oort cloud's boundary reveals the daunting obstacles looming. A trip past this threshold would require inconceivable amounts of energy and duration, well exceeding present-day technological limits. This limit isn't solely a material obstacle. It serves as a beckoning, a quiet summons to venture into the uncharted. With the unseen confines of our solar system now in focus, another query arises. Precisely, how expansive is it? Grasping its magnitude starts with examining the gaps among its worlds. Travel from tiny Earth to mighty Jupiter already demands a colossal trek, yet extending to the Oort cloud's fringe balloons that span into realms nearly beyond conception. Proxima Centauri, our nearest stellar companion, rests just 4.2 light-years off. Even so, the figures themselves overwhelm. Voyager 1, moving at a velocity that's remarkable by our standards, would require roughly 75,000 years to cover that distance. That's a duration exceeding the whole history of human society. The issue of time goes beyond simple physics. It's a deep idea that influences how we view the world. Can people really wait millennia to see the outcomes of venturing beyond our stars? Time isn't merely a steady stream. It curves and distorts based on speed. Einstein's relativity of time explains that as something nears light speed, its time passes more slowly compared to the rest of the universe. This creates a remarkable opportunity. Should we create tech for nearly light-speed journeys, might the way humans perceive time change completely. In the years ahead, with progress in innovation, we might find methods to bridge these enormous gaps, making visions of star-hopping voyages come true. Yet to make it happen, we need to tackle the puzzle of time head-on, a vital element woven into our drive to master the universe. Launching into the space between stars means a vessel has to escape the pull of gravity from its starting world and eventually from the sun. This calls for a precise boost in speed, called delta V. Escaping the sun's hold from Earth's orbit requires a mind-boggling delta V. Propelling any sizable craft to those velocities takes an enormous surge of power. Right now, this reveals the biggest flaw in our tech. Chemical rockets, strong enough for lunar trips and solar system probes, prove wildly inefficient. They don't provide the sustained power or push for extended trips outside our local star area. To push past this obstacle, researchers are exploring cutting-edge engines like ion thrusters, nuclear fusion systems, and even the hypothetical warp drive. Ion thrusters, firing charged particles for a continuous but mild acceleration, outperform chemical ones in efficiency. Still, their weak output limits them to solar system tasks, not reaching star-crossing paces in a lifetime. A more exciting but tough option is propulsion via nuclear fusion. It aims to mimic the sun's core reaction, merging simple atoms to release tremendous power. If achieved, it might offer revolutionary thrust, letting ships hit incredible speeds. The downside: mastering fusion for reliable Earth power is still a top scientific challenge. Shrinking it into a ship engine is a whole other level. The most daring idea is the warp drive, a concept that would curve space-time around a vessel, permitting travel beyond light speed while obeying physical rules. For now, ships use a smart tactic: gravity slingshots. By swinging close to a planet's gravity, craft like NASA's Voyager pick up velocity for free, whipping around Jupiter to build momentum. But even this smart trick only boosts speed by a few kilometers per second, far short of what's essential for star travel. The void between stars holds hidden threats in its wide emptiness. Beyond the sun's shielding heliosphere, probes or crews would endure a barrage of cosmic rays and energetic bits, mostly protons and dense atomic cores. These can punch through ship walls, wrecking gear, and worse, harming people by mutating genes, increasing cancer odds, fogging the mind, or causing fatality. Voyager 1, for instance, met unfamiliar magnetic patterns upon leaving the solar system. Factor in the freezing depths of that space, and the difficulty intensifies. Crafting shields that guard equipment and life without excessive weight is a massive design challenge. Interstellar regions also contain sparse wisps of gas and grit. Though thin, at high velocities, a speck of dust turns into a supersonic projectile that could shred a hull. Countering such fast collisions requires revolutionary materials, ones that repair themselves or endure massive hits. A subtler but tough issue is staying in touch. Signals via light or radio move at limited paces. As a craft strays farther, delays in sending and receiving grow, especially to the nearest star, Proxima Centauri. A radio signal would require more than 4 years to get there, resulting in massive lags for sending instructions and receiving information. Keeping steady contact over these immense spans while dealing with disruptions and weakening signals continues to be an unresolved enigma. Together, these factors turn interstellar voids into territories where unseen obstacles go beyond mere engineering hurdles. They become questions of sheer existence. Overcoming this expanse demands far more than robust propulsion. It calls for novel substances yet to be invented, revolutionary protective barriers, and the resilience of people to withstand the universe's most brutal conditions. Researchers are ceaselessly expanding tech frontiers, fueled by the aspiration to open pathways to extraordinary explorations in the far reaches. Among the grandest proposals is Breakthrough Starshot, an audacious scheme for deploying thousands of minuscule probes, each no heavier than a handful of grams. Fitted with vast light sails, the initiative aims to blast intense laser arrays from our planet to propel these sails to incredible velocities, reaching as much as 1/5 the speed of light. Traveling at such a pace, a single nanocraft might arrive at Proxima Centauri in merely 2 decades. Equipped with imaging devices and instruments to relay findings back to Earth. Daunting technical obstacles persist, from constructing lasers capable of delivering continuous thrust to keeping the sails steady and guaranteeing reliable links over those colossal gaps. Still, this endeavor shows that our species is starting to look past the restrictions of conventional launch vehicles. Venturing even deeper into speculative territory are ideas like warp drives and wormholes. Alcubierre's warp drive offers a sophisticated theory, warping space-time to enable superluminal journeys while respecting local rules of physics. Wormholes, by contrast, suggest portals slicing through space-time, creating conduits that might connect remote cosmic locales. At present, each demands exotic states of matter unseen in nature and lingers solely in the domain of abstract theory. Organizations such as NASA, ESA, and JAXA, alongside trailblazing firms like SpaceX, are collaborating to stretch the edges of what humans can achieve. Exchanging expertise, combining assets, and aligning on shared goals will prove vital, since venturing to the stars isn't a solitary country's goal. It's the shared aspiration of all humanity. One of the most daring ideas for such voyages is the generation ship. Far from a simple craft, it embodies a deep emblem of optimism and our species' persistent urge to reveal the universe's secrets. This concept arises from a stark truth. Trips to the closest stellar neighbors like Alpha Centauri might span dozens or hundreds of years. Thus, a generation ship must nurture life across successive lineages, forming an independent habitat that can uphold a full community during the stellar trek. A prime difficulty involves sustaining a balanced, sealed biosphere inside the vessel's limits. Experts are investigating setups where essentials like water, atmosphere, and nourishment get reused and refreshed solely from internal supplies. Efforts such as Biosphere 2, a sealed habitat trial in Arizona, provide a preview of these trials. A compact environment forced to recycle air, water, and provisions without outside aid. Securing long-term resource cycles, handling refuse, and fixing breakdowns across centuries or millennia pose issues without historical parallel. Even a minor air leak might spark devastating outcomes. Power generation forms yet another vital element. Options under review include nuclear fission, solar power, and nuclear fusion, the stellar core mechanism itself, as viable means to fuel extended expeditions. If harnessed, fusion could deliver endless, plentiful energy, slashing dependence on standard propellants and bolstering the feasibility of these monumental odysseys. However, the toughest trials may well be human rather than mechanical. Mental and communal strains. Solitude, restricted spaces, and the complexities of close-knit groups in a fabricated habitat will challenge our limits in unforeseen manners. How do people fare when whole lifetimes pass without glimpsing a true starry expanse or sensing a breeze against their skin? In what ways will we handle routine, evolving traditions, and the sure rise of disputes in prolonged isolation? Can the founding purpose endure, or will it erode under the weight of mere continuance? Studies on team behavior in harsh settings, from polar outposts to brief orbital stays, yield key lessons. In the end, the vision of a generation ship goes beyond mere technological achievement. It represents a profound exploration of our core identity, the principles we hold dear, and the lengths we'll go to secure our role in the cosmos. Here we stand on the threshold of a revolutionary boundary, the intersection of biology and technology. Can humankind adapt through evolution, or must we undergo total transformation to endure? Normally, evolution is a gradual phenomenon spanning eons, but in the realm of interstellar voyages, this pace might be compelled to quicken dramatically. Studies indicate that our species has inherent genetic adaptability to shifting surroundings. Take, for example, high-altitude populations who often exhibit enhanced physical features, like expanded lungs that optimize oxygen intake. In a comparable way, exposure to elevated radiation or reduced gravity in space habitats could spur the development of novel genetic adaptations for resilience. Among the most severe hazards of deep space is cosmic radiation, an unyielding energy that harms DNA, leading to illnesses and deteriorating health. To mitigate this, genetic modification for bolstered radiation tolerance is now a topic of earnest debate. Picture future spacefarers engineered with advanced DNA repair mechanisms, immunity to cancer, or tissues and organs built to resist fierce radiation levels. This concept has transcended the boundaries of speculative fiction. Tools such as CRISPR-Cas9 are unlocking remarkable opportunities to reshape the human genetic code. Residing in microgravity settings presents yet another critical hurdle. Observations of space travelers reveal that extended periods without weight cause muscle wasting and reduced bone mass. In the long run, such conditions might foster evolutionary shifts towards slimmer, yet durable skeletal structures, optimized for feeble gravitational forces. Even more audacious is the prospect of merging human and mechanical elements. Should our biological forms prove too vulnerable to space's rigors, why not augment or supplant them? Cyborg entities, blending organic and synthetic components, could withstand radiation, brutal cold or heat, and the void of space far better than purely natural beings. Envision a person's mind housed in a sturdy robotic frame, or even assimilated into a comprehensive artificial intelligence network. Should AI evolve to achieve true sentience and autonomous enhancement, it might emerge as the ideal pioneer for cosmic odysseys. Unlike us, machines shrug off radiation, need neither air nor sustenance, and could operate without flaw across vast timescales. They could embody the ideal voyages for timeless expeditions. Yet this raises a sobering dilemma. If we reshape our DNA to an unrecognizable degree or trade our bodies for metal, what endures of our human spirit? Notions of self-awareness and meaning will be tested to their limits. Venturing past our solar system isn't solely about seeking fresh planets. It may evolve into a transformative odyssey to redefine our essence and decide if we're prepared to sacrifice facets of ourselves for the unattainable. Interstellar journeys won't unfold in the coming decades or centuries alone. Enormous obstacles, ranging from physical and engineering feats to biological and societal ones, loom large. Approaches like the generationship concept or re-engineering our biology bring weighty moral and existential dilemmas that we must face head-on. Still, it's precisely this aspiration to shatter boundaries and touch remote stars that captures the essence of humanity. It reflects our fundamental drive for exploration, insight, and self-elevation. From our earliest societies, we've gazed at the enigmatic night skies, pondering our cosmic role. This unyielding inquisitiveness has propelled advancements in knowledge, innovation, and thought. At its heart, space travel is an inward quest for understanding. Even if we don't venture beyond the solar system for thousands of years, the pursuit of those truths ignites our deepest impulses, urging us to evolve, aspire, and persist without end. In this eternal pursuit, we may uncover richer purpose in our place amid the enigmatic universe. Downward, blazing warmth, success in the descent, blazing warmth, blazing warmth. Yo, yo, yo. Let's push forward. Yo, sweetie, blazing warmth, blazing warmth. That low orbital drift, gradually forming across eons, reveals the delicate framework. Blazing warmth, blazing warmth, blazing warmth, blazing warmth. Blazing warmth, blazing warmth, blazing warmth, blazing warmth, blazing warmth, blazing warmth, blazing warmth. Blazing warmth, utterly smitten, glory be. Blazing warmth, 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 blazing warmth.